Set of notes here to explain how to do some half-life problems. This is actually something you've done before in biology even. I taught you guys how to do this a certain way. I want you to do it a little bit differently now. So I'm going to change it a little bit on you because you have to understand that some of the ways that we tried before aren't always going to work. Just because I have numbers that come out cleanly, I'm going to get a whole number answer for grams here, doesn't mean that that's the way it works in real life. So you need to be able to solve this no matter what, not just when you can divide by 2 and it comes out evenly. So we're going to do some half-life problems. When you see it set up in this format, I'm essentially telling you that you're starting with 448 grams, and I want to know how much is left after 6 half-lives. And a long time ago, I told you guys how to do this. In biology, you could have just taken 448, divide it by 2, and you're going to get a new answer, 224, and then divide it by 2 again, and just keep dividing by 2 6 times, right? So it goes from 448 to 224 down to 112 now, down to, that would be 56 next, right? Down to half of that is 28, and I don't know how many times I've divided by 2 already, so 1, 2, 3, 4 times. I need 2 more. So I'd go to 14, and then I'd go to 7. 7 should be my answer, 7 grams, but that's not actually how I want you to do this anymore, right? I want you to do it using some math, right, an equation, so you can come up with this answer no matter what the half-life is, and no matter if that starting number is divisible by 2 or not, right? In order to come up with a clean answer like this, I had to have a number like 448, because if it was 449, I'd have some decimal answer for the final one over here, right? So it's not always going to come out so clean. You can't always do it this way without a calculator. So I want you guys to use an equation that looks something like this, right? I have an initial amount, and I'm going to take it times 1/2, and I'm going to raise that 1/2 to a certain number, and that number is going to be the number of half-lives. So in this case, it was 6. But again, I'm just setting this up. If I take the initial times 1/2 raised to the half-life power, I'm going to get some final amount of that stuff. And so what that would look like, right, I'd have 448 times 1/2 raised to the 6th power. And I can punch that into my calculator. So you should try that. Use parentheses for your 1/2, raise it to the 6th power. You can also take a 0.5 and raise it to the 6th power if you want to. It's the same thing. But in your calculator, without having to do each step here, because you might be using a calculator anyway. Maybe you can't do 448 divided by 2 divided by 2 maybe that's not something you're good at doing in your head. So it's actually much, much faster to know how to set up this equation and get an answer, because it's just going to spit out 7 for you, right? So I want you to know how to get that final amount, but I'd also like you to do it this way so you can practice using that math with your calculator, because it's much, much easier actually. Unless I'm only asking you to divide 2 or 3 times, it's actually inconvenient to divide 6 times by 2. So using the equation, see if you can come up with answers. Otherwise, this next one is backwards, right? I'm telling you how much you're going to end up with, which should have been a gram amount, but that's all right. I'll add that label now. And I want to know how much I started with. So this is the opposite. Instead of dividing by 2, I'm going to multiply by 2, right? And I can still use that equation from above, right? The only difference is in my calculator, I would start with the final amount, right? And I would actually divide by a 1/2 raised to a certain power. In this case, it's going to be 4, right? And that would give me my initial, spelling that funny, amount. So on your calculator, I'm going to need to do that real quick. I didn't do it on the last one because I already came up with the 7 answer. But if I start with that final amount, 13, and I divide by, in parentheses, 1/2, raise that to a 4th power, that's going to give me an answer of 208. So again, I just punched it in, simply 13 divided by, and I use parentheses, 1/2 raised to that 4th power, and I got an answer of 208. Right? Nice, easy, got a simple answer. Right? I could also multiply by 2 4 times, but I'm asking you to try and learn how to use your calculator appropriately to get an answer for something like this, because sometimes it's not a whole number answer, right? So it's not always going to work out nicely. I'm going to have it work out nicely for these problems just so that you know that you got an appropriate answer, because if you get a weird looking number, that means you probably did something wrong. But otherwise, there are definitely examples where you're not going to get whole numbers as an answer. So work it out using an equation. There is actually one more version of this. This one is a little bit tougher, right? I told you in the past that you could divide by 2 as many times as necessary to get from 160 to 5, right? So, and just count out how many times you divided by 2. But I actually want you to do that differently now, right? So I had that original equation. I got this initial amount times 1/2 raised to that power, the number of half-lives, is equal to my final amount. If I want to solve for that number of half-lives, if I want to solve for an exponent, that's possible. I just have to do a little bit of algebra, right? And I'm going to have to use a button on my calculator that I possibly haven't used before, right? So I actually start out by dividing that initial amount over. So I actually have final over initial on the right side. And then I'm going to do something to both sides of this equation. Now, you may be in trig now and you're going to learn about this later, but essentially if you want to solve for a power, if this is my variable that I don't know, I actually need to take a log of both sides of this equation, because what that's actually going to do is I'm going to rewrite this. That's going to pull that exponent out front. When I do a log of that 1/2 raised to a power, the exponent gets pulled out front. And then I have something that looks like this. Right? And then finally, to get that exponent all by itself, I take that log, again, I'm going to start shortening this, final over initial, divided by log, undo that last thing, log of 1/2, and that's going to give me my power, right? So I know that seems complicated, but now that I've already written that out for you, you can just write that down and use that over and over again. But essentially I take, okay, I want to know the number of half-lives here. I take log of final over initial, so that's 5 over 160, right? And then I divide it by log of 1/2. And what that's going to do, again, is going to give me my number of half-lives. And it should be a whole number in this case. So I'm trying that my calculator right now. Log 5 over 160. It depends on the calculator how you're supposed to use that logarithm button. So you need a scientific calculator. You might have to look for one on your Chromebook. But divide now by the log of 1/2. And I could just punch in 0.5, but I'll put 1 divided by 2 inside the parentheses as well. Right? My final answer, though, gives me a nice clean whole number. It's 5. So I have 5 half-lives. That means that if I divided 160 by 2 5 times, I'd get to 5, which you can check that to make sure it's true. 160 turns into 80, turns into 40, turns into 20, 10, 5 after 5 times of dividing by 2. And yet, in this case, it almost would have been easier to do it that way. But it turns out that even that exponent is not always a whole number, right? When we talk about half-lives, and I said that we're going to use that for something like carbon-14, carbon dating, right? There is no, like, there's no way that that thing that's really, really old, that died a long time ago, died in an exact increment of some 3,000 odd years for it to get to today. So if we want to know a non-multiple of that big number of years, right, how old something is, we have to have decimal answers for our half-lives, right? It's not always a whole number. That's my power. So this is the only way to solve it if it's not a whole number in this case, right? So you have to know how to do it. Again, practical example with, say, carbon-14. So real quick, just because I forgot it for the time being, what's the half-life of carbon-14? Let's see what it is. 5,730 years, right? I was way off. I was thinking it was 3,000 for some reason. But anyway, right? 5,730 years. This way I don't forget it. That's how long the half-life for carbon-14 is, right? And this is what a carbon-14 dating type problem would start out like. Because really, you have a certain percentage of carbon-14 in your body because you take in carbon every day, and that amount is relatively constant, right? It's only when you die and stop eating, stop taking in nutrients, that amount starts to drop off. So all living things start out with a certain percentage of carbon-14 in their body, but that percentage is really, really tiny, as you can see here. It's 1.5 times 10 to the negative 10th percent, right? That's a 0.0000009 zeros followed by a 1.5, right? That's how much carbon-14 you have out of any carbon sample in your body. That's how much of the carbon would be carbon-14. That's barely anything, right? But over time, that amount is going to decay. This 10 to the negative 13th is smaller than the 10 to the negative 10th. So it's going to decay over time. And what I want to look at is, okay, I just measured this sample and I see that this percent of carbon-14 is left. How long has it been since that thing died? So again, I'm going to use that same equation that I just talked about, right? I'm going to do the log final over initial divided by log of 1/2. And so I'm going to take log of final was this 1.46 times 10 to the negative 13th. Excuse me. And I'm going to divide by 1.5 times 10 to the negative 10th. Right? And I can just plug all of that into my calculator. But again, it might be a good idea to come up with an answer for that first and then do a log of it, right? Because I know I can kind of eliminate some of this stuff, right? So if I'm going to divide by 10 here, all I'm really going to do is turn this 10 to the negative 13th into a 10. I'm subtracting plus negative 13 plus 10 is going to give me a negative 3 power now. And I can do the 1.46 divided by 1.5 in a calculator on its own. And I get a 0.9733 whatever, right? So I can just do a negative log. Excuse me, pushing the wrong button on my calculator. Negative log. I keep saying that wrong. I'm going to do a log of whatever's going on in there. And again, I could just punch it all in. But I got this 0.973333. I can just throw a bunch of those in and then take it times 10 to the negative third power. Close my parentheses for that log. And then divide by log of 1 over 2, 1/2, or I could do 0.5 again. Right? But when it's all said and done, I'm going to get this answer. And because that was an indeterminate number that I punched in, the 0.973333, whatever, right, I'm going to get not quite a whole number, but it's really, really close to 10, right? So I just found out how many half-lives have gone by, and it's not necessarily exactly 10, but it's close enough in this case. And again, in real life terms, living things die in increments less than 5,730 years, right? It's not like everything that's died that we find a fossil of is some power of that, right? Something died 6,000 years ago too, and we might want to know that, right? Or whether it was 8,000 or maybe 22 million years ago, right? It doesn't have to be some multiple of 5,730. That's the only way this would work if it was always whole numbers. That's not the way real life works. So you're going to get some answers that are non-whole numbers, but again, in this case, it was a nice whole number because I intended it to be. But what this means ultimately for us is that 10 half-lives have gone by. So I actually have to take that 10 then and multiply by 5,730 to figure out how many years have passed. So if 10 half-lives have gone by, that thing died 57,000 years ago, 57,300 years ago, right? That's what this half-life ultimately helps us with in our carbon-14 dating, right? Once we know how many half-lives have passed, we know how long ago that thing died. So again, kind of complicated. You wouldn't have to do one of these on the worksheet that you're going to get, but maybe I could do something that complicated on a quiz, right, or a test. So just make sure you understand how you would do it. All right, so that should be good for the notes here.